Good morning, everyone. Thanks for taking the time to sit in for part 3 of The Future is Bright for in-bin grain drying. My name is Glenn Wilde. I'm with Top Grade Ag, and Top Grade Ag is a ag tech startup, and our vision is to make on-farm in-bin grain drying the preferred method of grain drying for farmers, and we feel that our IBD monitor is a key piece to this, I guess, to get us on this path. And we also feel that this webinar will provide a lot of valuable insights into in-bin drying to help facilitate this transition. Today's topic is basically an overview of air delivery systems and how they impact the in-bin drying efficiency. We got into significant detail in part 2 on airflow and why 1 CFM per bushel is a critical threshold that you really should be above. You know, the higher airflow, the better. And we also got into some detail as far as aeration fan selection. And with that review, we sort of found that that most fans operate most efficiently with a static pressure of somewhere in that 6 to 10 inches of water, and that's where we get the best bang for our buck as far as the fan moving a good volume of air. So what that really means is that we have 6 to 10 inches of pressure loss is all that we can really, our air can experience. And today we're going to go through, essentially there's 3 components that introduce air loss into the air. The first is the air delivery system, so the ducting, how we get the air into the grain. There's some pressure loss across that. The most significant pressure loss is through the grain. We'll touch on what causes that pressure loss and how we can have an impact on reducing the pressure loss through the grain. And then finally, it's just getting the air out of the bin with proper venting. So the first item would pertain to the air delivery system, and a really important concept is louvered area. And the simple definition is the surface area of aeration ducting having perforations to allow air to flow through. So this is something that is typically quoted, and really this, just to give you a bit of a feel, here's a rough schematic of just a standard rocket air delivery system. And the rocket has two louvered areas. They have an outside louvered area, and the air enters, goes directly out into the grain mass, and then there's an inner louvered area, and the air goes into that center hole. Now, this all is considered louvered area, but what I want to introduce is the term effective louvered area, and I'm going to refer to that as ELA on my diagrams. But the definition for that is surface area of aeration ducting having perforations to allow airflow with an unrestricted path to the grain mass. And there's an important differentiation there, in that this is where you are just counting the louvered area that is going direct into the grain. So with this example of the grain guard, or with the rocket, you can see that the outside louvers are directly going into the air mass, but the inward louvered area is going into I guess, effectively into a dead end. And the way out of that dead end is either going upwards or going down. So it has a slight reduction in the overall louvered area because it isn't an efficient path for the air to follow. So I'm gonna be doing some rough calculations for a number of different air delivery systems. And again, these are just to give you a bit of a feel for how the different systems compare. I haven't gathered this data off of any manufacturer's website. It's just basic math, and hopefully you understand. It's just directional sort of guidance. Now, the first aeration system that we're going to look at is the full floor aeration system, and this is the most efficient system out there. The full floor is louvered, and I'm using an 18 foot diameter bin, so about a 5,000 bushel bin, and that works out to 254 square feet of louvered effective louvered area, which is I guess that is the optimum. That's as good as it gets. You can't get any better air contact with today's technologies. The second one that we're going to look at is just a simple aeration tube. This one is a 24-inch diameter tube and 8 foot long, which again is sort of standard for 5,000 bushel bins or a 18-foot diameter. And that calculates out to about 50 square feet of louvered area, and that is roughly 1/5 of the louvered area that you would get with a full floor aeration bin. So you can see that you can justify a lot bigger fan and move a lot more air into a full floor bin than you can with a simple aeration tube. Here's an example of how the effective louvered area of a simple aeration tube is sometimes not what it appears. These one of the downfalls with the simple aeration tube is that they aren't self-cleaning. So ultimately, the chaff will build up over time, and you will lose effective area. You can see in this example, you probably have at least a 10% reduction in louvered area, and that is going to happen over time. I also did a simple aeration tube calculation for an 18-inch aeration duct, just to give you a feel how that reduces our square footage. And you can see that calculates out at 38 square feet. And 18-inch ducting is very typical for the smaller bins, and it's also very common for 3-horse fans. Typically, the 5-horse and 7-horse fans would be on the 24-inch ducting, but the one real critical thing is that when you go down to a 30 to an 18-inch, you physically can't get those high airflow rates through that ducting, and you will end up with significant air loss if you upsize a fan. In many instances, you'll be thinking that you're going to get significant additional airflow, but in many instances, if you have too low of square footage, no matter how big the fan you put on, your airflow will be restricted, and in many instances, you'll just burn up the electricity that you're using to run your fan in friction. The inverted trough is a very common air delivery system. It basically is, it technically doesn't have any louvers. It's just an open bottom to a doghouse. And essentially the louvered area is the cross-sectional area of that bottom. Now, once grain fills that bottom, it acts as if it is louvered, and you will get significant pressure drop because ultimately it has to flow through that grain. Now, the trough itself isn't giving the pressure drop, but it's more so the reduced area and the higher velocity that grain has to enter the grain mass. So So instead of being injected aerially in a simple tube, all the airflow is going directly down, so you have a very high velocity, and that tends to cause significant back pressure. But the 24 square foot, it does show to be somewhat inferior to the simple tube. But again, the bigger impact isn't the fact that you have pressure drop getting into the airway, but it's more so that the cross-sectional area is so small that you have a very high velocity, and the initial contact with the grain is at a higher velocity. The louvered inverted trough is an upgrade to the just the basic louvered trough, and it has an addition of additional airflow passages on the top of the trough. And again, just using very basic calculations, I come to about 36 square feet. Again, I think these numbers are likely, you have less resistance than you might in the simple 18-inch tube, but it gives you a bit of a direction that it would probably be somewhat comparable. And really, ultimately, in order to get real data, you almost have to have an IBD monitor or capture static pressures on comparative bins. But this is a directional sort of analysis. Now, when you go into the premium air delivery systems, the cube is one that is becoming more common. It has a luxury of very high louvered area and effective louvered area, which I've given it about 83 square feet, which sets it above most other air delivery systems. And it does seem to have a significant advantage when it comes to surface area. The retro rocket has a 50 square foot effective louvered area, and I briefly touched on some of the inefficiencies because of the fact that some of that air is being injected inwards instead of into the grain mass. But even with that, this is a really effective method of getting good airflow into the heart of the bin, and it stacks up really well. In many instances, this is the go-to air delivery system. The Gatco is a new higher tech premium system, and it actually has sidewall vents that inject the air into the bin. It has about a 48 square foot effective louvered area, and that's assuming that we have 12-inch by 12-foot sidewall vents, and 4 of them spaced equally around the bin. So again, it compares comparably with the rocket and with the 24 by 8 simple tube as far as cross-sectional area. And the last item is the T-rocket. This is a modified rocket that Wilde Ag Ventures has been developing, and really all it is you tee into your simple tube with a vertical 18-inch, or actually in this instance it's a 15-inch vertical rocket, 8 by 15, and you can see you basically are adding to this 50 square feet, and you're getting an additional 32 square feet. So it's an additive, and all of it is effective. You're injecting air right into the heart of the aeration bin, which gives you good air to grain contact. Now, with all these different systems, the real key is measuring your static pressure. Now, for some of them, namely the simple aeration tube, the T-rocket, and the cube, you can literally put your static pressure gauge on and start up your bin empty, and see what your pressure loss is. See If I like to be at 1 inch or less with the just basically injecting directly without any grain. With the inverted trough and the rocket, that's not an option because they're self-cleaning. They aren't an enclosed system, so there really is no back pressure when you have no grain in the bin, and ultimately you really, in order to get a feel for the performance of those systems, you need to have your tube covered, and then you get a better feel for the effect of louvered area and the impact it has. The full floor aeration, you really can't do that test on. Manufacturers do not recommend running a full floor aeration bin without any grain in it, and you are risking doing damage. But ultimately, you really need to do comparative analysis with the different systems, and in order to do that, you need similar grain of similar moisture with the same fan operating on 2 bins with a different aeration system, and that really is the best way to understand the advantages. Now that goes through basically us getting air into the grain mass, and now we're going to walk through basically our friction losses going through the grain, and this is the most significant. Probably 80% of the losses would be going through the grain mass. Each grain has a different friction factor, and I mean, all farmers are aware of this fact. Peas and corn and soybeans have a very low friction factor. You can move lots of air, you can fill your bins, whereas flax and mustard and canola are very small seeds, and you really have to be careful not to fill your bins too full because it has a very high friction factor. Friction is affected by chaff and weed seed, so that core will impact airflow, and you really should be aware of this. There are I guess technologies out there. The grain spreader is one that comes to mind, and it basically levels out your grain mass, and it eliminates that core. Other ways of addressing it are really focusing on getting good airflow through the core of your grain bin, and that is my preference to deal with it. It just is, I guess, a simpler method, but there are lots of ways of addressing this, and it's just important to be aware. Longer airflow path increases static pressure. This is probably the most important item that you have to be aware of, and you really have to address this. You know, in a full floor aeration bin, or I guess in any aeration bin, the easiest way to reduce your airflow path is to reduce your grain depth, and that's where having your static pressure gauges on your ducting, so that when you're filling your bin, and then you can monitor your airflows as you fill the bin, it basically prevents you from overfilling it and causing too long of a flow path, and that really is as difficult or as complicated as it is. It's just, if it has too far to travel, it's going to have too much pressure loss. One interesting item that some of the companies are exploiting is the fact that horizontal airflow is lower, horizontal friction is lower than the friction with vertical airflow, and that, you know, there's been significant research done, and what it really points to is that, for example, oats, if you push air through oats horizontally instead of vertically, you get about a 10% reduction in the back pressure, or the pressure drop. Now, if you move to wheat or canola, you actually get a 50% reduction in the pressure drop, which is really astounding. And barley is even more pronounced at 70% lower. Most of this research has just been done not on farm. So again, this is just paper data. It's not, I wouldn't consider it real data yet, but it is, it's compelling. And there are some companies that are basically using this concept to add new technologies. The last item about grain friction is that higher velocity air causes higher friction, and that's where I mentioned in the inverted trough, if you have a smaller area where all the air is forced to go in the same direction, you will end up with a higher pressure drop there, and ultimately the key is to spread out your airflow throughout the bin as best as you can to make sure you don't have any real high velocities at any point. So now I just want to walk through those same air delivery systems, and this time I'm going to focus on two items. One is the accumulation of moisture due to the drying front, because that is a pet peeve with all farmers, and most air delivery systems just have to deal with that fact, but there are some systems that are trying to eliminate that problem. And the other thing is basically the length of the airflow path. Different air delivery systems can modify how far the air has to travel to get out of the bin, and I'm just going to touch base and sort of discuss how those the different designs impact how far the air has to travel. The first one again is the full floor aeration. This one, obviously the air has to travel 100% vertical, and the airflow path is fixed by how full you fill your bin. You don't have any control over that. The drying front is going to be horizontal, and it will accumulate moisture at the core. That's just like most air delivery systems. That's just one of the downsides of in-bin drying. So you will very likely have to move your grain in order to get rid of that core. The one scenario that gets around this core is the introduction of a stirring mechanism in a full floor aeration bin, and this is a really common and quite effective way of eliminating that core and actually enhancing the airflow by stirring the tough and the dry grain, and that is a common path for farmers to take is converting their full floor into a stirring bin. Now the simple grain tube or aeration tube, it again, if you look close at the airflow path, you've got, say, a quarter of your air is going out the top of the aeration tube, but it's going out radially in all directions. And if you look at the worst case scenario, or the air that is being pushed out the bottom of that aeration tube, you can see that air has to go down, turn around, and it has to come back up. And assuming this is 24 inches, you can see that air has to probably go close to 3 feet before it gets to the top of this grain tube. So you can see there's a percentage of the air here that is got a lot tougher path to take. And ultimately, when looking at air delivery systems, you want to find a system that provides an easy path for the air to get to all the grain and to get out of the bin by traveling through the least amount of having the least path. And you can see here that a quarter of the air here is traveling a very long path. So that's in part why the simple tube tends to be a little less effective than some of the premium systems. The other item is the drying front. Again, it has just a horizontal drying front. You do accumulate a core at the top of your bin, and moving is almost always required to prevent spoilage. The inverted trough is again, this is sort of an extreme case of what we just discussed, in that all the air is forced out the bottom. So we don't have the benefit of having some air going a nice short efficient path. It all is forced out the bottom. And not only does that introduce really high velocities in this area so that you have more friction, but it forces an additional 3-foot path for that air to get out of the bin. So that will add to the inefficiencies, and it just is something to be aware of when choosing which bins to do your in-bin drying in. Drying front is horizontal, and once again, you will accumulate moisture at the top of the bin, and you will have to move and blend your grain to prevent spoilage for winter storage. Here's the louvered inverted trough, and again, you can see that what they've done is they've added some louvers on top, so that introduces a path for air to exit the top of your air delivery system, and that adds significantly to the efficiency. So now potentially you can have half your air taking an easy path and only half having to travel the long tortuous path out of the bin. So you can see how this will impact your efficiency and will reduce back pressure. The drying front is unchanged. You will accumulate moisture at the top of your bin, and you will have to move and blend your grain for winter storage. Here's our first premium air delivery system, and it's the Cube. And as we have discussed, the Cube has very good louvered area. That there is some airflow is pushed downwards and in a less efficient path, but the lion's share of your air delivery is upwards or to the side. So this has should be a very efficient way to get air into the bin. I also like the fact that you are injecting a lot of air into the core, so that any of those fines that might be hindering your airflow, they're basically negated by having excessive air. The drying front with this system, and I want to also point out that these drying fronts that I'm putting on here, these are just my interpretation. There's nothing scientific about it, but I'm just trying to illustrate how I expect the moisture to migrate, and ultimately it migrates with the direction of airflow. Now with the Cube, I envision higher airflow in the middle of the bin, so I expect you would get less of a moisture buildup because you're going to have higher airflow here, and ultimately the sidewalls might have a little more moisture just because you don't have as much airflow on the bin walls. But again, this is just a qualitative analysis. The rocket is very similar to the Cube. Again, you've got very little airflow being injected into the bottom of the bin. Probably it's just enough to dry the bottom of the grain in the cone. The majority of this air is going outwards or upwards, and it also is up higher in the bin. So you have a nicely reduced path for this air to get out of the bin. Exactly the same as the Cube. You likely will get better drying in the core, so any fines will be a non-issue, and the drying front would likely look similar, where you would have the bin walls would probably be drying slower than the core because of the excellent airflow through the core. Here's an interesting, I guess, an adaptation of the rocket, and basically what they do is they add sidewall vents. Here's an image of a sidewall vent, and it basically is attached to the sides of the bin. Typically there are 4 of them, and the way this works is that the purpose is to try and exploit the idea of horizontal airflow. Now, the only way that you can get significant horizontal airflow is if you give the air a path to exit the bin on the bin walls. So the way that this works is you start with step 1, and these sidewall vents are open. So you'll start up and you will be injecting, the lion's share of your air is injected in a very optimum, sideways direction. It is going to try and travel the easiest path, which is horizontal. And as it hits these sidewall vents, it's going to exit. So what this does is, and what you would see in a system like this is, even if your bin is full, you would see relatively low static pressures when you have your vents open, and you would be drying the bottom portion of the bin first, and your drying front would likely be a vertical drying front, and it would move from the center of the bin outwards. Now, with this, oops, I got ahead of myself. Now with this, you get really efficient air delivery because of the reduced airflow path and because of the horizontal flow, but you also get the benefit of moving the moisture out of the bin quick. So instead of bulldozing all that moisture upwards into your attic and creating a core, it's exiting right now, and that way you don't accumulate the core like you would in other systems. Step 2 is closing the sidewall vents, and then you basically are blowing out the remaining moisture on the top portion of the bin just with your conventional drying front. And this is our first look at a technology that is exploiting the idea that horizontal flow is or horizontal friction is less than vertical in airflow through grain masses. Here's the Gatco tube with cross flow. This is another premium air delivery system, and again, it is focused on horizontal airflow. This system is focused pretty much exclusively on horizontal. The idea that horizontal friction is lower. You can see that you have extremely good air delivery. By the way it works, as I noted, you're injecting air into these sidewall vents, and then you've got your central vent pipe that provides an easy path out of the bin. So as air is injected into these, it's going to want to flow preferentially horizontal, and because you've got this easy exit, it actually will stick to that horizontal flow path. And the idea again is that you will get less back pressure, and you will get your moisture out of the bin quicker. Very similar technology or very similar theory as the sidewall vents with the rocket. The drying front in this instance would be moving from the sidewalls inwards. So you're moving your drying front, and the moisture is migrating towards that center tube. And again, with this, you wouldn't have as much of a core. So when you move this grain, it would likely move with very uniform moisture. But I'm just speculating that you'd get a nice uniform and blending wouldn't be as critical as when you have a real core at the top of your bin. The last air delivery system is a T-rocket with cross flow, and this is something that that we're developing at Wilde Ag Ventures on our family farm. And basically the idea here, as I had noted, we just added a 15-inch or an 18, but we've added 15-inch aeration on top. And you can see here, you still have some inefficient air taking a long path coming out the bottom, but the lion's share of the air that's being introduced has a very short path to get out of the bin. The real goal with this design is that we want any air that is injected to have a path out of the bin that is very nearly half the radius. So you can see here, this is a sidewall vent, and basically the air can flow horizontal straight towards us into this sidewall vent and out, and here air can flow up to the other sidewall vent and out. But no matter what path, whether it's from the top of the rocket out, should be roughly half a radius, and this is the type of design that would ensure a short airflow path. And the idea is to optimize your air delivery and reduce your pressure loss. With this system, the drying front would slowly radially move outward from the core. And again, I like injecting into the core. It just gives you the confidence that you are getting enough airflow, and the fact that core is a little bit more dense with the chaff, that you will get good airflow. So that summarizes I guess the real goes into detail with how these different air delivery systems work, and how different designs can enhance your system. The last item is venting, and we've now gotten our air into the grain mass, and we've basically passed through in as efficient a manner as we can, and now is bin vents, which is a very simple item, but it just can't be overlooked. You must have easy exit from the bin. And there are a couple of real rough rules of thumb: 1 square foot vent per 1,000 CFM, or 1 square foot vent per horsepower. I've seen them, and I'm sure they work. My preference is less of a rule of thumb and more of a hard number, and I like to say 0.2 inches of water pressure drop through the vents. And this is a luxury that you do have when you have an IBD monitor, because you know exactly what your delta P is with your vents. And I'm not saying that 0.2 inches is the only number. Really, with my choice of 0.2 inches, it really is a statement that I want it to be low. There's no reason to have high pressure drops through your vents. And I mean, you only have 6 to 10 inches of water to play with. And if you're going to sacrifice up to 1 inch for the air delivery, getting it into the grain, and if you are sacrificing very much on this end, you really are hurting the efficiency of your overall system. So with our IBD monitor, you can set this and you can have an alert sent out if it gets above your set point. And really, for the most part, I haven't seen too many bins with poor vents or poor venting. But the real, I guess the real area that I do see some concerns is wind blowing lids shut and your vents freezing up if you're drying with significant condensation. But it is important to be aware and to monitor that aspect of it. The last item on the vents is the idea of roof vent fans, and I just want to point out that these vent fans are not, the application isn't to reduce back pressure. The vent fan is designed to eliminate condensation when you're using supplemental heat, and I just we're going to touch base on vent fans when we do our webinar 4 for supplemental heating, but I just want it to be clear that that is not the idea isn't to reduce back pressure or to eliminate vent losses. Well, that brings to end webinar number 3, and we welcome feedback and questions through our website. Please feel free to leave any comments. And just in summary, I really want to stress that every one of these air delivery systems will work to dry grain in your bin. And ultimately, we really recommend getting a monitoring system on your bins so that you can analyze exactly what kind of performance, how many gallons per hour can each bin deliver, and what is the cost. And once you do that analysis, it makes a lot of sense to do your upgrades one bin at a time so that you can really see the step change, and it helps you justify if you're actually spending your money wisely. That way you know how much capital you put in and you know how much savings you've had. So anyways, once again, thanks for sitting in and participating, and I look forward to talking to you again at part 4. And part 4 will be focused on supplemental heating and fuel sources. So we will see you then.